Good afternoon, everybody. Welcome to Tuesday afternoon of Chem 1105 with your host, me, Dr. White. Hi, everybody. All right, let's start out with not Zoom, but some important things to remind you. Let me remind you that the amnesty program I have will end a week from today on August 1st at right before midnight, the very last minute or so of August 1st. Any labs you haven't handed in that have been due, hand them in. After that date, if it's past the deadline, you'll get zero. Yep, 0 points. I know I'm being funny, but in real life, it's not funny if you get 0 points. So hand in your labs. Do some, how should I say this, stuff that just came up, personal stuff. I got a little behind in grading labs. I'm catching up by Thursday noon. I'm making a promise to myself. By the way, each lab is worth 10 points. 10 points. But anyways, by Thursday noon, all labs that were due, I will have graded. If you've handed it in, I will have graded it. That's a promise I'm making to myself, which means tomorrow night, today I'm going to be busy, but tomorrow all day I'll be working on that, except when I'm teaching in my office hour. And I probably won't be able to go to bed until I finish on Wednesday all past labs. At that point, what I will do is put out an email telling everybody to check Blackboard to make sure that if you've handed in a lab, I've graded it. If I didn't, email me. Once in a while I'll miss one if you handed it in late, and I thought I'd go back and check because I have 20 people and we've done, 11 labs? That's a lot of labs to check. But anyways, I'll do it. And don't forget the amnesty. And don't forget, this Thursday, I'll be giving test number 4 online. I've already talked about it. Here's the information. You should have gotten an email a while ago. And I'll be doing that on Thursday. And you'll have until Friday to finish it up. It covers chapter 7, acids, bases. And today I'll finish the organic, which I'll keep my promise to myself. 2 classes are the same as a week in the fall and spring. And by finishing up today, it gives you, quote unquote, a week to practice. Tomorrow, I will spend a better part of the day going through the organic chemistry problem set, 2 organic chemistry practice problems with you, and 3, I'll do my review for the next test, test 4. One thing I'll try and do tomorrow or today, I haven't posted test 2 video privately and sent out an email. I'll get that handled today by the end of tonight. And with that, what were we going to do today? Well, first of all, we're going to do our lab, the last lab of the semester. Yay for some of you, I'm sure. And then I will finish up organic. And if we have time, I may even start on the review. All right, let's get to today's lab. And today's lab deals with fundamentals of chromatography. And chromatography is a method to identify things in organic chemistry. In my grad school, I did a lot of similar type of chromatography for reactions I did. and you're going to learn about paper chromatography, what is the retention factor, which everybody just calls RF factor, and how you determine if something is one substance or a mixture of substances. And one way is to use paper chromatography. Now, there's other types of chromatography, which I've also used. One is called gas chromatography, called GC. And then there's high pressure liquid chromatography, HPLC, which when I was in grad school, I actually built one of the first HPLC units at Michigan State, because I thought that would be neat to learn how to do that. And it was. All right. Now, if you notice here in the background, they talk about how when you see a color, that could be from artificial colors, which most colors are. And these are different chemicals that are put into products you purchase. We call them also dyes. And there are different dyes here, like blue number 1, blue number 2, and yellow, green, and so on. Now, paper chromatography is an analytical method. That means a way of measuring something where you can separate very small amounts of a mixture by dissolving them in a liquid known as the mobile phase. And remember, none of this will ever be on a test. And what happens is that on the paper, the mobile phase moves the molecules of the material you're testing up the paper. Now, paper has what's called hydroxyl groups on it that are polar, and different molecules react different ways to those hydroxyl groups. So different molecules, if you pick the right solvent, go up that paper at different rates. So you can separate if it's a mixture. If it's just one pure compound, it won't separate. And here they talk about polarity, like I said. And here's the hydroxyl group in cellulose, otherwise known as paper. And less polar spend more time in the solvent and go up further. Polar things are slowed down by the hydrogen bonding to the OH group. Now, the retention factor, RF, is calculated by the distance the solute travels divided by the distance the solvent front travels. And it's always less than 1 because the longest distance traveled will always be the solvent front. And this is one way of identifying things. If they have the same RF value, then those are usually the same compound. Now, in today's lab, you're going to use some dangerous stuff. Kool-Aid, paper, your micropipettes, and the other equipment they have over here. Now, you're going to be using these food dyes. Wear gloves. When you're doing this, do not touch your face or anything with your gloves on. Because if you get food coloring on your skin, it's going to take a long time to get off. Time for a Dr. White story. Back when I was in grad school, postdoctoral fellow Dr. Plavin had a Halloween party. It was a lot of fun. Dr. Plavin, Larry Plavin, and his wife had fun parties. And I went to his house. I forgot what I went as. I think I went as a samurai or something like that. And this one couple won the award for the best costume. They had togas and they had little antennas. They had little lights on top, and all their skin here and here and here were green. They came as Martians and they looked great. And then Larry asked them, how'd you do your skin green? Did you use, what's the term? acting dye or cream. There's another name, I forget. And they said, no, we use food dye. Oh, no. It took about 2 months for it to wear off their skin and face. They're walking around green. I got back from Larry with a couple. They were driving down the street a week or two after Halloween in green, and a policeman pulled up like that. Didn't pull them over, but the moral of the story is be careful with food dye. Don't get it on your skin, or it's going to take a long time for it to wear off your skin unless you wash it immediately. I mean, immediately. Anyways, it was, I can still remember this. I hate to say this, but what year was that? It was about, oh, I shouldn't say this, but I will. I think that was 1975. Wow. That's almost 50 years. I have a photographic memory. I can still picture them, and I can still picture when Larry asked him, what did you do? And the look on his face, and probably mine too. No, not food dye. It isn't going to come off because they'd already had it on their skin for an hour or so. All right, back to the lab. Now, what you're going to be doing is, now here you need some table salt, sodium chloride. You have the kosher stuff, that's the better one to use, because other salts have things like potassium iodide in there. That shouldn't throw it off. You'll need a pencil. Do not use a pen, because that will mess up your chromatograph strips, because ink is made up of different chemicals. A pencil, which is essentially graphite, will not go up a chromograph or your paper. And here are the things. Now, you don't need M&M candies because you will be not doing, if you look at the blackboard, you will not do activity 3. This you will not do with the M&Ms or a pen. 1 and 2 is enough. All right, let's go through what you have to do. Now, your chromatograph strips, you first have to cut in half, and then here they have an arrow. You don't have to cut the arrow, just have the bottom square. And each strip, and you can wait before you cut it in half, 1.5 centimeters up, put a line across with a pencil, not a pen. That will ruin this lab for you. Next, 9.5, 9.4 centimeters up, you put another line. Then you'll cut it in half, and you'll have to do this for a number of strips. Now, the micro pipette, about 5 centimeters up from the tip, you'll cut it because you need the tip. Now, you could also use toothpicks to do this, but this is a better one. We used to use glass melting point tubes instead of tips of eyedroppers, and you'll need that. All right, now, on a paper towel, put your chromatography strips and place a small plastic bag or piece of aluminum foil on top of another paper towel. In separate locations on the plastic bag or aluminum foil, put a couple of drops of the dye. What they're asking you to do is make a little container, either with the plastic bag. If I were doing it, I'd use the aluminum foil. And you put a couple of drops of each of the dyes, red, yellow, and blue. On a serious note, if anybody is colorblind, let me know. I'll help you out with this lab. When I worked in the chemical industry at 2 different companies, each one, I had a chemist who was red-green colorblind. And for certain tests where it was a color change, he'd have to have another chemist help him because he just couldn't see that at either company. But anyways, then you take one of the micro tips and dip it into the little cup you made with aluminum foil, say with the red dot. And then on the lower line, you'll put a dot of that. And then you'll repeat that by doing a couple of times. You dip it into the red dye with the tip, put it on the paper, the same place. So you see a nice little dot there. And here they have a way you can look on this video to see how to spot that. Now, you'll repeat 4 and 5 with the other dyes on separate strips. And so you'll have 3 strips, each one with a nice dot at the line at the 1.5 marker. Now, place 3 test tubes and add 20 drops, or about a milliliter water, or 0.1% sodium chloride solution in each of the tubes. Now, how do you make a 0.1% sodium chloride solution? Well, I would take your graduated cylinder, weigh out 200 milliliters of your water, put it in a beaker, and then weigh out 0.2 of a gram of sodium chloride. Put that in the beaker, use your spoon or whatever you want to use to mix it so it's all dissolved, and that will give you a 0.1% sodium chloride solution, and enough for this lab. Now, what you'll do, use the straight pins they have at the top, above the very top, you'll punch a hole through it, and this will hold the strip in the test tube. And what you'll do is, in each test tube, you'll add about 1 milliliter of water of the salt solution. Then you'll put the strip in there and wait until the liquid goes up to the upper line. You'll see the water salt solution go up. And it should be straight in the tube and all that. That's important. And then once it gets to that top mark, the liquid, not the colored dot, take it out. And then put it down on a paper towel or something and mark the leading edge of where the solvent was and where the drop, anything that goes up color-wise, and measure the 2 distances. From the line at the bottom to where the solvent end is your solvent. From the line at the bottom to where the dot is the distance of the solute travel. And that upper number divided by the bottom will give you the RF factor. Now, what that will look like will not be like you see in the lab. We've done this similar lab and face-to-face. I've had students, it doesn't really work out that well. Shh. But just do your best, okay? Remember, shh, don't tell anybody I said that, but don't get frustrated when it doesn't look like the pretty pictures you might see online. All right, now, you'll fill out this table. What color was the band that went up? Hopefully for red, it was red, and so on. What was the distance the band traveled? What was the distance the solvent front traveled? And divide the band distance by the solvent distance, you'll get the RF factor. Now, this number will help you identify things in the next lab or next activity. Now, what you'll do is take 3 more strips where you mark 1.5 at the bottom and 9.4 at the top with a pencil, not a pen. And then for each of your Kool-Aid solutions, they tell you previously where to prepare it, and I missed that. Let's see. Here they tell you I was right. They say 100. I would make 200 just to be safe. Now, with the Kool-Aid, you weigh out 2 grams in the weigh boat on your scale, then transfer it to a labeled plastic cup. You've got the small ones, and add 5 milliliters of water. And you do that for each type of Kool-Aid. I missed that. Well, I found it, so I didn't totally miss it. And then what you'll do is take a clean, and if you want to do this, the micro tips you used in activity 1, rinse them with water a couple of times, so you can do it this one. And what you'll do is 1 strip, you'll take each type, the orange or whatever order you want to, and just like you did in activity 1, put the tip in the Kool-Aid, put a drop on the line in the center of the strip. Do it a couple times till you see a nice little dot on the paper. And you'll do that for each of the 3 Kool-Aids. And then you'll put in the pin at the top, put the salt water in the 1 milliliter into the test tube. And you should clean out your test tubes before you do it. Rinse it a couple times with water. And then you'll lower the strip in there. The pin at top will hold it straight up, and you'll wait until the solvent front goes up. Now, if you notice, it says it takes about 15 minutes. This doesn't happen instantly. Same thing with the other one. Then remove it once the solvent gets near the top, and then let it dry a little, and then mark the different bands and measure the distance for if there's more than 1 band, each band, and then also the distance the solvent travel, and measure those, and you'll be able to fill in this table. Now, if there's more than 1 band, which there might be, say band 1 traveled this distance, the solvent should be the same for all these, and the RF value. Now, how do you identify what the dye was for that dot? You go back and look at this table. If it's RF, and let's just say red 40, the RF was 0.5. I'm just picking a number out of my head. See, 0.5. Oh, it's Bad Humor Tuesday. That was pretty bad. And if you come down here and say one of these bands was very close to 0.5, then that's the red dye number 40. And if we say yellow was 0.3, and I'm just pulling it out of my head again, I got a lot of numbers in here today. That was really bad. And if you see one of these dots here, 0.3 in the grape, then you know that was that. And you do that for the others also. Now, listen carefully. Do not, I like my hand signal. No, don't do activity 3. Now, if you want to, I'm not going to stop you, but you don't have to do it, and I'm not going to grade it. All right. Now, for the write-up, you'll just recopy the data from table 1. Then you'll list 3 and increasing polarity. The most polar travels the least distance. And then here you'll identify this, and you only have to do 1 photo. They have you do a lot of them. Now, explain how the colors of strawberry, orange, and grape are made. hint, mixtures of some dyes. You got to figure that out. I'll say that again in slow motion. Hint, mixtures of dyes. All right. Now, that's today's lab. Now, when I was in grad school, we used a different type of chromatography, similar. Instead of paper, we had on microscope slides what's called silica gel or alumina. And for the kind of molecules I was dealing with, not dyes, that would help us follow when something was made where you had a known or your starting materials when they disappeared. So you could tell how long a reaction has gone and is it done yet. And every Monday morning when I was in grad school, I would get to my lab. And the first thing I would do was, because it was cheaper and we made them better than the ones you store bought, I would make about 100 microscope slides, and that would last me through the week. And I wasn't the only one who did that. All right. Any questions? Don't forget, hand in labs. This is the last lab of the semester. You've got the rest of this week and good part of the weekend and Monday and Tuesday to finish up. If you need help, come to my office hour or email me. And if I can, I'll set up a private Zoom meeting with you. If you need help for anything else, I'll do that. All right, let's get back to organic chemistry. I want to finish this up. Now, in organic chemistry, you will find that they're general reactions. And what I mean by general reactions is when you do something to a certain functional group or type of molecule, that kind of reaction will always give the same type of products. In a way, if you look at that door over here in my office, I know I can go from one room to the other. Now, in your house, the doors look maybe different trim, whatever, but you know it goes from one place to the other. And if you came into my house, my front door looks different than this, but you know that's a place to go through from one area to other. Same thing with your car door. It looks way different than that, but you know it's to go from one area outside the house to inside. Well, different types of reactions with functional groups give the same type of products, just like you know what a door will do. The first thing I want to teach you is combustion. And combustion is when you burn something. And we'll do the one for saturated hydrocarbons, like propane. Now, this is the general reaction right here. That's Subtle Tuesday. Now, how do you use this? Well, first of all, unless you're calculating how much of a certain chemical you react with another to make a third chemical, organic chemists who are lazy when we can be, don't balance equations. So this one I'm not going to balance. So what am I going to do? Well, by the way, this is propane. And this is the reaction that happens when you cook on a barbecue. Now, The question is, how do I know what to do? Well, you look at this molecule and say, oh, that's a saturated hydrocarbon. It's a molecule with only carbon, hydrogen atoms and carbon, carbon. Atoms. And with oxygen, it always gives carbon dioxide plus water. This is my general reaction that you have to learn. Well, you don't have to, but if you want 4 points, you better. And what's the answer? Carbon dioxide plus water. And this is the beauty, and I mean really the beauty and power of organic chemistry, but now I'm being biased because I'm an organic chemist. So what if I put this on a test? And the question would be, what's the product or products for this reaction? Well, I don't expect you to know this, but this is butane. That's the liquid in those small lighters. But butane is a saturated and I'm going to use abbreviation hydrocarbon. We're reacting with oxygen, and I know with the spark, you'll get carbon dioxide plus water. You'll also get heat, but that's not a chemical product. And therefore, butane, which is a saturated hydrocarbon, reacting with oxygen, guess what that will bring? Carbon dioxide and water. And it's time for you to try one. And the question is, what are the product or products in C? Your turn to have some fun. I see somebody already got the right answer. Yay! But everybody else, I'll give you time to figure it out on your own, so I don't want to steal the fun from you. Oh, everybody's done. Now, let's look at this molecule. This is called octane. Where have I heard of octane before? At my local gas station. You buy gasoline with the different octane numbers, and it has different isomers, and that's different molecules with these carbons and hydrogens. And octane is a saturated hydrocarbon. And I'm reacting with oxygen. And guess what you get? Carbon dioxide plus water. And therefore, octane is a saturated hydrocarbon. I will get carbon dioxide and water. And that's the beauty of general reactions. Once you know this general reaction, you can apply it to specific reactions, and about 99% or 98% of the time, that's what you get. For this reaction, it's more like 100%. Now, when it doesn't get what you want, then that's my level PhD stuff. How do you make it work right? But that's not for this class. Now, a favorite trick organic chemist instructors do on tests is put a big, scary molecule. If you can't look at it and identify what it is, you go eek and don't get the right answer. Hopefully none of you go eek. But let's try one of these big, scary molecules. Remember, there's always 4 bonds to carbon, which is how I know how many hydrogens to put in. When I teach organic chemistry, for those of you who know science fiction, I'm putting in my hydrogens at warp drive, which means very fast. And I tell my students, if I make a mistake, let me know. And the same question. What are the product or products for that reaction? 4 points each. If you're not done, just wait to hold off on saying yes until you are. Let me relaunch. This way, I'll wait until everybody says yes for me to continue. Well, everybody said yes, so I can continue. Now here's this, oh, look, a big scary molecule. No, it's just got carbon, hydrogens, and carbon-carbon single bonds. That's what this is, a single bond. And therefore, this is just a saturated hydrocarbon. I'm reacting with oxygen. And what do you get? Carbon dioxide and water. And therefore, what am I going to get here? Carbon dioxide and water. Now, how many of you have ever been behind a car in the winter and you see coming out of the tailpipe a liquid? And you think, oh no, it's leaking gasoline, it's going to blow up. No, it's not. In the winter, a car that just starts out, its muffler and tailpipe are still very cold. When it heats up, it turns the water from this reaction here into a vapor you don't see. But when it's cold, that liquid coming out is the actual water. Now, it's never going to get cold enough, at least while we're alive, to have the carbon dioxide become a liquid. It will always be a gas. But that's what you're seeing coming out of the tailpipe. So you should be able to do this type of thing. Now, the general reaction right here, you need to know. Now, on a test, some of my best students, when I teach organic, always write the general reaction underneath the problem, like I did. And some of my best students never do that, but both of them still have it here. They've memorized it. Now, how do you memorize this? Well, you can use flashcards, and frankly, I don't like flashcards. They never work for me. Write down saturated hydrocarbon O2 arrow CO2 plus H2O and say it, saturated hydrocarbon oxygen gas is CO2 and water. Do that 5 times, 1, 2, 3, 4, 5. And then a day later or two, do it again 5 times. And it's going to be burned into your brain real good. All right, let's look at another general reaction I'd like to teach you. And that's called hydrogenation. I will never ask you what is hydrogenation, but it's the addition of hydrogen gas to an alkene. And I have a triple bond too, but for now, let's just keep it to double bond. It's a double bond, and what you need a catalyst. Now, catalyst, platinum, palladium, or nickel, is something that makes the reaction go quicker, but is not consumed in the reaction. And if you didn't use a catalyst, you'd have to wait a couple of months for a reaction like this to happen. With a catalyst at 140 degrees, it's done in 4 hours. How do I know that? Because I've worked with this reaction in industry. In fact, one of my first research projects was using this reaction. Now, what I have here, this is a way of drawing any double bond. R means carbons like X and Y. Another way of showing it would be double bond, hydrogen gas, catalyst, You break one of the bonds. This is called a pi bond, and I'll never ask that. The other is sigma. You break pi bonds like that, and each carbon of the double bond gets a hydrogen. Now, let me review something I haven't done before. You can write a chemical reaction, A plus B plus C make D. Remember, these are the reactants, these are the products. Now, organic chemists are lazy, and we are at times, and sometimes that same reaction will write this way. A reacts with B and D to make a B and C to make D. And that's what I'm doing here because I'm an organic chemist. And the catalyst can be platinum, palladium, or nickel. Because nickel is way cheaper than platinum and palladium, in the chemical industry, you use that. In research and academics, we use platinum and palladium because you got research money. All right, let's look at how to do this. How are we doing time? We're doing good. And the question is, give the product or products to the following reaction. And you look at the starting material. Do you see something that's not carbon, not hydrogen, or carbon-carbon single bond? And the answer is yes, there's a double bond in red. And the rest of the molecule, carbon-carbon single bonds, other than combustion, don't react. They come along for the ride. So I can look at this and say what's really happening, double bond, reacting with hydrogen. Nickel is a catalyst, and the catalyst can be platinum, palladium, or nickel. And you break one of the bonds in each carbon of the double bond. These carbons gets a hydrogen. Now, listen carefully. Do you break carbon-carbon single bonds? No, except for combustion, you don't. It's rare. So notice here I start with 1, 2, 3, 4 carbons. Guess what? I'm going to end up with 4 carbons. But I break one of the bonds of my double bond. Notice there's only one line. Each carbon gets a hydrogen. Now I know there are 4 bonds to carbon, so I can put in my rest of my hydrogens. This carbon has a hydrogen, 2 bonds, 3 minus 4 minus 3, 1 hydrogen. This carbon has a hydrogen, a carbon-carbon bond, 4 minus 2 is this. Now you can write it this way, but if you look at this carbon, it's really got 2 hydrogens on it. So I could also write it this way, and this carbon has 3 hydrogens. Now I'd suggest you write it this way. It's one last thing you have to do to get wrong. All right, let's do another one. And I'll do this one. And the question is, give the product or products for the following reaction. In this case, it's not an saturated hydrocarbon because look, you have a double bond. So that's the key functional group. That's where all the fun's going to happen. I'm reacting with hydrogen gas, H2. What's platinum? A catalyst. Remember, the catalyst can be platinum, palladium, or nickel. In this case, it's platinum. And you break one of the bonds of the double bond, and each carbon gets a hydrogen. Now, do you break carbon-carbon single bonds except for combustion? No. Therefore, I have 1, 2, 3, 4, 5 across. 1, 2, 3, 4, 5. And this carbon, I have this carbon, it's called the methyl group. Now, the two carbons of the double bond, these two, I broke a bond to make a single bond between them, these two. And each one will get a hydrogen. So I'm going to do that. And now I know to put the rest of the hydrogen, because there's 4 bonds to carbon. And that's how you do it. If I look at the clock, I've got time for one more. And I'm going to let you have some fun. You try that. Give the product or products for the following. Remember, vote yes when you're done. Do not vote no. All right. Look for what's different. Ooh, a double bond. So the rest are carbon-carbon single bonds, and they're not going to react with hydrogen, but a double bond reacting with hydrogen and a catalyst. Remember, the catalyst can be platinum, palladium, or nickel. In our case, it is nickel. You break one of the bonds, and each carbon of the double bond gets a hydrogen. You break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 carbons across. My product will have 5 carbons across. These 2 carbons here, notice I broke one of the bonds because that's what my general reaction shows. Each one gets a hydrogen. Now I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And that's how you do it. If I look at the clock, it's time for a break. Let's take a 5-minute break. I'll see you in 5 minutes. You know what I'm going to do, get up and stretch. Time to get going. All right, we're talking about reaction of double bonds with hydrogen gas called hydrogenation. And the general reaction I have here, and you should be able to do something like that. Let's do one more. Let me get that image on the screen. Oops. All right, here are the general reaction, and 4 points each. Give the products for the following reaction. And let's do one more. And the question would be, give the product or products to the following reaction. 4 points each. Your turn. Remember, just say yes when you're done. If you're not, hold off on saying yes. And please be patient. Try and give everybody time to finish. And everybody's finished. Isn't it nice that Dr. White's patient? All right, how do you do this? Look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like, ooh, I see a double bond. And the rest are just carbon and hydrogen single bonds, which under these conditions aren't going to react. So what I really see is a double bond. That's what the two lines reacting with hydrogen. And what's palladium, PD? A catalyst. And the catalyst can be platinum, not in this case, palladium, yes, or nickel. And you break one of the double bonds, and each carbon gets a hydrogen. Do you break carbon-carbon single bonds except for combustion? No. So I have 4 across. On this carbon here, I have my 2 CH3 groups. They come along for the ride too. But here's my double bond. I broke one of the bonds, and my general reaction shows me each carbon of the double bond, after it reacts, gets a hydrogen. I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And that's how you do it. Now, when I teach Chem 1212, which is the 1 semester organic here at COD, which I've taught many, many times, students, I teach them about 55 general reactions like this. Now, I have a PhD in synthetic organic chemistry. I think I know about 450 or 500 general reactions. Now, when I teach organic, one of the questions I always ask students to ask of me, or they should in their own mind ask, why am I learning this? Well, the obvious answer is someone said you have to take this class to get a grade to get into school or program. Well, why learn this stuff? Well, let's take a look. Not at me. And let's talk about the history of peanut butter. And peanut butter, which I can take it or leave it person. There are other things I like better, but it's nice. And peanut butter has been around for a long time. But something happened back in the 1920s, and this one doesn't have it. I found it earlier. Now it's Murphy's Law saying you're not going to find the one I think this is the one. Now, earliest peanut butter, you couldn't store that long because what happened is there would be a layer of fat or oil on top formed, and it wasn't too appeasing or appetizing. And then what happened was I can't find it, but around 1930, a chemist, here it is, 1920s, Joseph Rosenfeld found that if you partially hydrogenated oils, fats and oils, and mixed that in with your peanut butter, it stayed homogeneous. And this became what was known as Jif peanut butter. And that revolutionized the whole peanut butter industry because now you could ship peanut butter anywhere in the United States and it wouldn't separate. So when you go look at your peanut butter, you'll see hydrogenated or partially hydrogenated fats and oils. And I won't get into it too much in this class, but fats and oils, certain ones have a double bond. When you add hydrogen to it, you make a carbon-carbon single bond of that fat, and that makes it help keep the peanut butter from separating. Interesting. But you didn't know chemistry is involved in your food, big time. All right, now I'm going to turn the switch off for the next couple of slides. I'll tell you what it is. I just want to give you a feel. Fats and oils, and I worked in that industry. That's organic chemistry. If you like carbohydrates, the good stuff, French fries, potato chips, or other, pasta. I just gained a pound or two thinking of that. Yeah, Dr. White. That's carbohydrates. That's organic chemistry. If you like protein, if you're a vegan, tofu, soybeans. If you're not, hot dogs, hamburgers, steaks, ribs. You can tell I'm not a vegan, even though I do like tofu and soybeans. Now, things that are important are things like polymers. Those are molecules that are huge, made up like a train. You've ever seen a freight train where you have the same boxcar over and over again? Well, polymers that way, but like different groups of atoms. An example of polymer is the plastic of this bottle. And finally, steroids, which you also known as your hormones. That's all organic chemistry. Again, click, switches off right now. Now, when we talk about fats and oils, the key molecule in a fat and oil is called a triglyceride, which is still off. And when I first went to a new medical group and I had a new doctor back about, this was about 2014. And unfortunately, he had to retire because of his own medical problems. But Dr. Cantor was great. I went in for my physical starting with this new group. And with Dr. Cantor, I was told he was the best, and he was at that time. I now have another doctor since he retired that is really good. She's really good. But anyways, they did various things, including testing your blood for triglycerides. And he called me in. I got a call from the office and said, Dr. Cantor needs to see you soon. I said, all right, I can come in next week. He said, all right, we'll set up an appointment. And I love Dr. Cantor because he was always very direct and honest with me. And he said, well, here are your blood tests and your triglycerides are so high. And also at the time, my blood pressure was so high. And he said, quite frankly, you're in the 95 percentile group. And I said, for what? That you won't be alive in 5 years unless we change things. That got my attention real quick. And I brought down my triglycerides, and that was almost 8 years ago. And good news, I'm still alive. Now, what's a fat? What's an oil? Again, switches off. A fat is a triglyceride that's a solid or semi-solid at room temperature. An oil is a liquid at room temperature that's a triglyceride, or also known as a triester. If you've ever seen olive oil or vegetable oil at room temperature, that's 25 degrees C, it's a liquid. How many of you have ever made bacon? If you don't clean out the liquid that's in the pan while it's hot, what happens? It becomes a solid. And that liquid, once it cools down, that's a fat. That's pork fat. Now, I've worked in this industry, switches really off, and different types of fats and oils are in our daily life. Beef fat is called tallow when it's used in the chemical industry. There are two different types of pig's fat, yellow grease and white grease. And you have the oils. You're familiar with olive oil, corn oil, soybean oil. Now, there's an oil that's used throughout most of the world called rapeseed oil. You can't find that in the United States, rapeseed oil. Why? Because the American housewife wouldn't buy it. And where's a place that makes a lot of rapeseed oil? From the rapeseed? Canada. And someone very smart who was working for the group that organization of rapeseed oil producers came up with the idea, well, if the American housewife won't buy rapeseed oil and it's made in Canada and it's an oil, why don't we call it canola oil? If you go into your supermarket, you can buy canola oil, which the rest of the world calls rapeseed oil. Now, I work for a company that used tallow and yellow grease and white grease to make molecules that were then used to make things like your soap, your fabric softener, and a lot of other chemicals. And we would buy the plant I worked at and the research. I was in charge of all research for North America and quality control for this plant that was located and still is there, 47th to Racine, Chicago. Every week, we would buy combined about 2 to 3 million pounds a week of tallow and yellow and white grease. That's a lot of chemicals. Now, switch is still off. If you take a fat or oil and add acid and water, you get back what's called fatty acids and glycerin. Not to scare you, but this goes on in your stomach. When you eat something with fat or oil, that's how your stomach breaks down the fats and oils, the fatty acids and glycerin that your body uses to build things. Now, click, switches on. Better than that, how does soap work? Well, soap is made up of, and this part you don't have to know, switches off, something called surface active agents. These are chemicals that react or interact at the surfaces of different things. And it's shorthand, the name are called surfactants. And Dr. White's a world authority in surfactants because 3 of the companies I worked at made surfactants and helped people use them. Now, how does soap work? You should know what's the structure of soap. Now, I'll show you this right now. As soon as I get the right color. Soap is a long molecule with what's called a nonpolar tail, and I'll explain what polar is. Well, I already did, nonpolar tail and a polar head. And what some of them look like, you have CH3 and 16 CH2s connected in a long line. And then at the end, you have what's known as a carboxylate anion. This part I'm drawing here, you don't have to know. But this is my polar tail, nonpolar tail. And this is the polar head. But what you should know is that soap has that structure. It even says, know this. Now, the important thing, how does soap work? You should remember, like dissolves like. You should know this. First of all, you should know the structure of soap. It has a nonpolar tail, polar head. Now, I've taught you already, water is polar. And now I'll teach you dirt and grease are nonpolar. And if you notice, if you had dirty hands, real dirty hands, you take water and go like this under the water, they'll still be pretty dirty. So how do you do this? And remember, I taught you the key to this puzzle, which I'm going to go to a really large font because it's so important. Like dissolves like. And, well, how does this happen? Well, let's look at a little piece of dirt. Say it was right here. And I go get my soap and water and go like this. And the nonpolar tail, because a like dissolves like, is attracted to the nonpolar dirt. The polar head wants to stay far out. And this happens with a lot of molecules of soap. I'm only showing a few. You'd have at least a mole of that as soap, maybe, 6.02 times 10 to the 20, totally surrounding the dirt. You should know this is called the micelle. Now, another picture of a micelle I'll show you, or a better drawing, looks like this. This blue is the micelle. They cut out a portion so you can see in the very center, you have the dirt. And you can see the lines of the nonpolar tail toward the dirt. And on the outside, the negative charge with a counter ion is the polar head. And these are called micelles. And it even says on here, know this. Well, with the polar heads being on the outside, all around the dirt here, the micelle, and you should know this, looks polar to water. And water says to the micelle, I'm polar, you look polar, let's go down the drain together. And they do. And that's how you get the dirt off. So let's review this again, because on a test, if I ask, how does soap work? You should know how to answer it. You should know how to draw the structure, general structure of soap, nonpolar tail, polar head. You should know water is polar, dirt and grease are nonpolar. The most important thing of how soap works is like dissolves like, which I taught you for test 3 you had to know. That is things that are polar on solid polar things that are nonpolar are soluble in nonpolar things. You mix the two together, they're not soluble. And that's where the surfactant soap has, because it has both a nonpolar part and a polar part. And here you should know the structure, how to draw a micelle. That's dirt in the center and the tails toward the center and the polar head on the outside. And you should know now that since the polar heads are totally surrounding on the outside the dirt, the micelle looks polar to water, and now the micelle and water are miscible or soluble and go down to drain together. And earlier today, when I was washing my hands with soap and water, I was thinking, oh, I'm making micelles, and that's how I'm getting my hands clean. I was probably the only one in my suburb who was thinking that today. But then again, I'm an organic chemist and worked in this area. Now, a number of years ago, one of my students in 1212 came up to me and showed me an ad from a magazine. And if you see on your screen, now there are a number of products called micellar water or cleansing water. Guess what? There are no micelles in there. When do you get the micelles? When you use this to clean your face, like for makeup and things like that. And my female students have told me it works really good, these products, for cleaning stuff off like makeup. And when you put it on your face to clean off something, that's when you make the micelles. Because guess what? There are no micelles in micellar cleansing water. And you can tell your friends and neighbors and really impress them, and loved ones too. Now, let's go back. And if you look on your screen, typical soap called Irish Spring deodorant soap, and you'll see sodium palmitate, sodium palmitoate, and sometimes you'll see sodium stearate and others. And those are the soap molecules. long non-polar tail and the polar head. And really, that's what you do. And they also put a fragrance in there and things to make it smell like nice and feel nice. But let's try one more. And I hate to break this to you, but bar soap, I can't find what I'm looking. Let's see. Here's a bar soap, sodium lauryl isocyanate, stearic acid, sodium taloate, sodium palmitate. Those all come from, I'm going to ruin your day, but what the heck? That all comes from beef fat and pig's fat, unless you buy one that says made from vegetable oil. Guess what? There's nothing wrong with it. By the time you have it, it's been so reacted with chemicals that it's not the original beef fat, or you're not putting beef fat or pig's fat on your skin. Yeah, I wouldn't even do that. But anyways, a lot of things in your life that you use, like your fabric softener, started from beef fat or pig's fat. And I worked in those industries, so I know it for a fact. All right, let's continue on. But seriously, you should know, how does soap work? You have a non-polar tail, polar head. You should know how to draw the structure of soap. Water is polar. Dirt and grease are non-polar. The key to all this, and that's why I wrote it in big font, like dissolves like. And because of that, the dirt, non-polar dirt or grease, but I picked a dirt particle, attracts the non-polar tail of the soap. And the polar head is on the outside, surrounding the dirt. And now the micelle looks polar to water, and water says to the micelle, hey, I'm polar, you're polar, let's go down the drain together. And they do. So next time you're washing your hands, your dishes, or clothes or whatever, you're making micelles that help get rid of the whatever you're trying to clean. And you should know that. Hint, double hint, big hint. Now, another thing I want to teach you that how does a towel work? Your hands are nice and wet, or your arms or whatever, your face, and you take this magic device called a towel, or you could also, paper towels work the same way. And you go like this or wipe your hands, all of a sudden you're dry. What happened to the water? Well, don't write this down, but here's the structure of cotton. The N means these two things are repeating like boxcars in a freight train. And if you notice on here, I have these hydroxyl groups, lots of them. And just like water, this is an alcohol, even though it's not the kind that will get you drunk. And because of the different electronegativities, there's a slight charge on the oxygen, negative. Oops, I got it backwards. Hold on, don't look. Dr. Waite made one of his rare mistakes. Don't look. Did it again. Uh-oh, it's messed up Tuesday. And water, as you remember, and because of this there can be a hydrogen bond and that's how a towel pulls water off you or off a countertop into itself. And you should know, how does a towel work? By hydrogen bonding to water. How does a towel work? By hydrogen bonding to water. Now, I'm going to teach you something because you're dealing with someone who's worked in this area, and that's how to deal with fabric softeners. Fabric softeners, and by the way, I have a number of US patents in this area. Fabric softeners I created. Some are still being sold. Fabric softeners make your clothes feel nice and soft. First of all, use the dryer sheet. Dryer sheets work way better than adding liquid to your washing machine. Now, have you noticed after a long time, sometimes your older towels don't work as well as new towels, absorbing water off you? Well, that's because the fabric softener with time blocks some of the OH groups from hydrogen bonding to water. And that's called re-wet, how well a towel absorbs water. You can actually, there are measurements and tests for that. And I invented a fabric softener that had outstanding re-wet properties. Well, to get your towels back to the way they were, wash them once or twice, but don't use a fabric softener. And that will take all the fabric softener that's blocking the hydroxyl groups off there, and your towel will work fine. But the key thing, use the dryer sheets. All right. Switch is going to be off for the next couple of slides, but it's something in the active course file that I need to cover. So this will not be on test number 4, but I'd still like to quickly cover it. Now, biochemistry, and I'm not a biochemist, but I do know some biochemistry, is the study of chemical substances found in things that are alive. But the functional group chemistry for organic molecules occurs the same way in your body. There's no magic going on. It's just more complex molecules. So whatever you learn functional group, like a double bond or other things that I don't teach in this class, happens the same way as your body as if you're in a laboratory or a chemical plant. Now, switches off. Carbohydrates are molecules that have poly, meaning many hydroxyl aldehydes or ketones, or compounds. Again, switches totally off when you hydrolyze it. Hydrolyze means acid and water. That means what's in your stomach. And here are the structures of glucose and fructose. Each intersection in the line is a carbon atom. And this is called the Fisher projection, which I teach in 1212. Now, glucose is the most abundant. It's also known as a sugar in nature. Your body breaks down carbohydrates in your stomach to make glucose, which your body uses for energy. Now, your body can also use fructose. Fructose is the sweetest sugar. And a number of years ago, organic chemists found a way to make high fructose corn syrup. If you look at a lot of the products, especially the pop you eat, drink, and other things you consume, it has a lot of fructose in it, or high fructose corn syrup. That's there for one reason. Make it sweet, and you say, ooh, this is sweet. I want to buy more of this and eat it. Now, one of the things that, again, switch is still off, but table sugar, you know, that white powder you put into your coffee, tea, milk, on your cereal, or wherever else you want to make it sweet, is called sucrose. And that's a glucose and fructose molecule, one of these connected together. And in your stomach, the acid breaks that down to make fructose and glucose, which your body uses for energy. That's another course, not mine. Now, starches are just a lot of glucose molecules held together, switched still off, and your stomach, they break it apart to the individual glucose molecules, not only in your stomach, but in animal stomachs too, which is why it's the most abundant sugar in nature, because just about all the food you eat, when you break it down, the starches makes glucose. Now, proteins are made of another type of functional groups, actually, too, called amino acids. And they're linked together to make proteins. When you have 50 or more amino acids together, you have a protein. And your stomach acid breaks them down into amino acids that are used things to make muscles. So I've been working out today. And other things. By the way, your skin is a protein, and you never want to get acid on it because it'll break it down and ruin it. Now, steroids are your hormones. Again, switches off, and they have this basic ring system, 6, 6, 6, 5. Hold on, I have to look up a couple of things. All right, give me a thumbs up if you see that structure on your screen. Actually, I don't have to even do that. Thank you. And this is the male hormone or steroid called testosterone. Each bend in a line is a carbon. Now these wedges end in a line, those are carbons too. And this molecule affects various things in our body, the male hormone. I'm not an expert in medicine use of these, but I know the structure. That the research group, when I was in grad school, my advisor, half the group were working on steroids, and I was working on another type of ring system called sesquiterpenes. Thank you. Now, this is the male, one of the male hormones, also known as a steroid. Here is progesterone. It has the same 6, 6, 6, 5 ring skeleton, but it has different things on it. Like this was not there in testosterone. It was this OH. And this is progesterone, one of the female hormones. And that is today's lecture. I think tomorrow will be better. I'm going to end a couple minutes early. Don't tell anybody I'm cheating you out of a couple minutes. Shh. But I'll be able to do tomorrow. First of all, I'll do the review for test number 4, which is this Thursday. I'll also do the problem set for organic chemistry section of test 4. And I'll also go through some more practice problems in organic chemistry. You should know for test 4. Oh, I gotta get this fixed. Anyways, there it's fixed for test 4. And then I'll do some more chapter 7 stuff. So you should be very prepared for test number 4. Whoop, I gotta get that fixed for 4. Ooh, this one does it too. But anyways, with that, I'm done for today. Remember how soap works. When you're washing your hands later today, you're making micelles because alike dissolves like. When you're using a towel later today to wipe, dry your hands or anything else, the water is coming off because of hydrogen bonding. Those are 2 things you should know leaving my class. Also the pH scale, what's acidic, neutral, and basic. It goes from 0 to 14. And I'll cover more of that. With that, I'll say, don't forget, hand in labs that are due today. Don't forget about the deadline for the amnesty program a week from today. And not to scare you, but a week from this Thursday will be the final. Now, good news, take a deep breath, let it out, take a deep breath, let it out. Are you relaxed? Next Monday, Tuesday, and Wednesday, I will spend the whole week reviewing for the final exam. And I also have, if you look in the practice problems, I have practice problems for the final exam. On Thursday, I'll talk more about how to prepare for the final exam. With that, I'm done for today. I'll say, Gang gesund, goodbye now. I stole that from Granny and the Beverly Hillbillies.